let's get into the rest. I think the next one we would do is number 36. And this is reversion 2. Number 36. What's the following statements about the molecule Bn is false? And it says to assume sp mixing. Now we can approach this, and I think we should approach this from both the valence bond theory and the molecular orbital theory. Now the valence bond theory is not going to tell us anything about paramagnetism, but it might tell us something about the bond numbers. Let's just see what it does. If we have Bn, then we've got 3 electrons here and 5 there, so that's 8 electrons, and we would have Bn. We have 6 left over. 2, 4, 6. And if we're trying to make a 2, 4, 6, that's going to be hard to do. Can't have 4 bonds. This one's probably going to be here because nitrogen's the more electronegative atom. So you would put the lone pair here, and boron would just be deficient. Okay, that tells you that you have 2 pi bonds, which would satisfy D. D has 2 pi bonds. So that's telling us that this one's true. If we go the other route and we set it up to do molecular orbital, and we leave off the 1s, like the sigma and the pi from the core level, and just start with the 2s, then we would have a sigma with a 2s and a sigma with a 2p. Now this is mixing, sp mixing. So we'd have pi next, wouldn't we? And then we would have sigma 2s. Then we would have pi star. That's 2p, sorry. 2p. Get my brain in order today. 2p and then sigma star 2p. Okay. So we can work from valence electrons again because we left out the 1s, the sigma, and the sigma star from the 1s. So this would still be 8 electrons. So we'd have 2 here, 4 there, that's 6. And we would put 2 here, that would make 8, right? All right, so this one is full. These 2 are full. And this one is full. Okay. So, is paramagnetic. Is it paramagnetic? That doesn't say. Yeah. No, paramagnetic is drawn into the magnetic field, isn't it? Right, so that's false. Well, that's the one we're looking for, isn't it? But it's diamagnetic. It would be drawn into the magnet. It would be repelled by the magnetic field. Paramagnetic is drawn into the magnetic field. If we go bond order, is bond order 2? Well, let's see. 2, 4, 6, 8. 8 minus 0 divided by. Wait a minute. Can't have a bond order of 4. Maybe I drew the wrong. Sigma. Hold on. Useful information. 2s sigma star 2. Oh, I left that one out. Yeah, that's my mistake. Let's move this one over. I left off the sigma star from the 2s. Right, so that means these two are going to be moved over here. That doesn't change that doesn't change A, but it does change the bond order because we had 2, 4, 6 minus 2 divided by 2 equals 2. Bond order. So that agrees with, well, no, it doesn't agree with this one. Because that says it has 2 bonds. And this says it has 3. But the bond order there, it says it's 2, so okay. It agrees with that one. Total number of electrons is 12. Well, yeah. If we consider 2 and 2, add 4 to 8 would be 12. That's true. Okay. And it has 2 pi bonds. I thought, did I calculate this one correctly? 2, 4, 6 minus 2, 2, 4, 6. 2, 4, 6, 8. Yeah. So that's 2, 4, 6 minus 2 is 4 divided by 2. That's the right bond order, but has 2 pi bonds. The only way that you would get 2 pi bonds out of that would be from the valence bond theory. Okay, so we had to do it both ways. Bond order says 1 pi bond. Well, there is some disagreement there between the two theories, isn't there? That was 36. Maybe that's why I put that one in there. 38. Cheat sheet. Which of the following molecules or ions is not paramagnetic in its ground state? All right. So we have A, B, C, E. And the choices are O2, O2 plus, B2, NO with no mixing, and F2. Let's see. Okay, so they're all from the second period. And so if we leave off the 1s molecular orbitals and just start with the, let's see if I can get it right this time. Then we have, we're assuming no mixing. Well, boron is going to have mixing. I see why they say, assume no mixing because 1 is on one side of that dividing line, 1's on the other side. But this one is going to have mixing. All right, so let's put the no mixing first. All right, this is going to be from the 2p, then we're going to have pi 2p, then pi star 2p. We may not need all of these, but I'm going to put them in anyway. Sigma star is 2p. Okay, so this one's going to be the same. I'm going to use both of those for this one. Boron is going to be 2s, and then we got mixing. Then sigma. That's probably all we're going to need for that one. And NO would be like this one. Okay, and then F2 would be no mixing also. So it would follow this example. All right, now the number of electrons that we're going to place in there, we're going to only use valence electrons. So that would be 6 and 6 is 12 electrons. This will be 12 minus 1, so that's 11. Boron here is 3 and 3 is 6. Nitrogen is 5 and 6 is 11 here. And then fluorine has 7 and 7 is 14. Okay. So 12, this is 2, 4, 6, and 4 is 10, and 2 more here. Okay. 2, 4, 6, 8, 12. This one's going to be 2, 2, 2, 4, 1. This one's going to be 2, 4, and then 2 there. And so we don't need this one. And this is going to be 11. 2, 4, 6, 10, and 11. So we don't need this one. Oh, wait a minute. We might need that one for fluorines. So this one's going to be 2, 4, 6, 10, and 4. Okay, so we won't need that one. Okay, so we got everybody set up. All right, let's see. Which of the following is not paramagnetic? So which one, let's see. These are all paired up. That one's paramagnetic. Okay. This one is also paramagnetic because it only has one. Unpaired. This one also has, that's paramagnetic. But this one. So that's full, excuse me. This one is paramagnetic because that one's unpaired. Right. This one is all paired up. This is diamagnetic. So E is the one that is diamagnetic, and the rest are paramagnetic. Now, if you want to get good at that better than I am, you're going to have to practice. But since I'm not trying to turn you into chemists, you've got useful information as the arrangements of a lot of them back here. And you can tell on this last page, dioxygen and difluorine are no mixing, and the left are mixing. So you can put things in order by looking at that table. 39. I don't want to erase that if I'm going to need it again. So I'm going to put 39 over here, just in case. In the molecular orbital description of CO, assume sp mixing. The highest energy electrons occupy anti-bonding orbitals. So, okay. So, assume sp mixing. All right, so sp mixing is going to put, well, we don't have any there with sp mixing. CO? Yep, CO. All right, assume sp mixing. So we're going to have sigma, sigma star from the two S's. And then we're going to have pi and sigma for the P's. And then we're going to have pi star from the two P's and sigma star, the two P's, correct? If we were not mixing, it'd be like that. Okay, so we got 4 and 6 is 10 electrons. 2, 4, and 4 is 8, and then 2 more. So, let's see, what are our choices? The molecular orbital description, the highest energy electrons occupy anti-bonding orbitals. A is false. That's false. 6 molecular orbitals contain electrons. 1, 2, 3, 4, and then we left out the 1s, sigma 1s and the sigma star 1s. So that's true. B is true. 2 unpaired electrons. Nope. And D, the bond order is 3. So it's 2, 4, 8. 8 minus 2 over 2 equals 3. Okay. Bond orbital description. Now, why did I say B is true? 6 molecular orbitals contain electrons. 6 molecular. 1, 2, 3, 4, 5, 6. Well, B is true also, isn't it? Bond order is 3, 4, 5, 6, 7, 8 minus 2. It wouldn't change with the 1s's because there's bonding, anti-bonding. They sort of cancel out. So this is 6 divided by 2 is 3. That's true, and D is true also. All right, so I got a problem there. Unless there's something, let me see if I'm missing something. All right. Okay. That's the correct molecular orbital, sp mixing, true. Highest energy electrons. Let's see. Occupy bonding orbitals. Highest energy electrons occupy antibonding. Okay. 5 molecular orbitals contain electrons. One, two, three, four. No, 6 molecular orbitals contain electrons. Right? If we put sigma 1s and sigma star 1s, but we counted all the electrons, then that'd be 14. We'd have 2 here and 2 here. Right? So 1, 2, 3, 4, 5, 6. All right, that's a mistake. Right? And there are no unpaired electrons. Bonding order is 3. All right, so that's why we're saying this is the true one. Oops. This is the true one. And we're saying this one's false, but it's not. Okay, that question's messed up. So it should be, let's see, 6 molecular orbitals contain electrons. That's true. All right, so B and D. I'm going to make a note in here for myself. B and D. Okay, carrying on. Let's see, 41. All right. I'll just draw them again if I need them. All right, which of the following statements about CO3 2 minus ion is false? That's the carbonate polyatomic ion. Okay, we might have to look at this one Let's take this one as a valence bond first. That would be the simplest one because we haven't done one this complex with molecular orbitals. All right, so we have valence 4 for carbon, 3 times 6 is 18 here, plus 2 more. All right, so we have 24 electrons, right? Carbon's in the middle, and we have 3 oxygens. So that's 18 left over. 2, 4, 6, 8, 10, 12, 16, 18. There we go. Used them all up. Okay, so we need to make, all right, this is a case where we would have to use resonance. In order to make an octet for carbon, we would have to take that, or we could do it from this side, or we could do it from that side. So we have 3 possible resonance structures for the carbonate anion. I'm going to just keep that one. I think we can just, with one, we can answer the questions. Orbitals on the carbon atom are sp2 hybridized. Yes, right? 3 groups, trigonal planar, sp2. We need 3 equivalent orbitals. So that's true. Let's see. A, B, C, D, and E. This one's true. The ion is expected to be diamagnetic. All right. How do I answer that one? Well, I'll tell you, this is a difficult question. What we're implying from this is that they're all paired, but we know from experience that that may not be the case, right? That says that they're all paired electrons, which would be, they would be diamagnetic. But the question is, what does the molecular orbital say? And this is too complex for us to do molecular orbitals, right? It was fairly simple to do the diatomics, even the heterodiatomics. But if we've got that many, it's going to be difficult to deal with molecular orbitals at this step. So we just have to assume for the moment that they're all paired, and that means it's diamagnetic. Let's see, the CO bonds are different lengths. No, they're all the same length. Excuse me. Yeah, they're all the same length. We just can't show it this way. We have to resonate between 3 different structures, and we're actually saying that the bonds are like, they're equivalent. So C is the false one. D says the ion has a total of 24 electrons. That's true. And then E, all the above statements are true. No, that's false. All the above statements are, well, we're looking for the false statement. All right, so that was a poorly worded question because you got 2 false ones. No, all the above. Oh, that's right. Yeah. Okay. They messed up again. All right. Hopefully, I won't do that on an exam. If I do, you call me on it. All right. 43. 42. Yeah, 42. How many electrons are involved in pi bonding in benzene? All right, here we have to take the simplest approach. C6H6. Benzene, remember, is a ring structure. Like that. There's a carbon at each one of these junctions. And in order to have this structure, we have to have 1 hydrogen at each position. Okay, now back to the question. How many electrons are involved in pi bonding. Remember, we form pi bonds by unused p orbitals. Right? So unused p orbitals are going to be sideways overlapped with each one of these. And when we do that, or this way actually, we've got 2 electrons. So we have 2, 4, 6. 6 electrons are involved in pi bonding here. Okay. When we draw out this simplest structure where we show the singles and doubles, then we can imply 2, 4, 6 electrons in pi bonding. But we know reality is a bit different than that. We have that delocalized pi, delocalized pi bond for the entire molecule. It's kind of a hybrid approach. Okay, 45. Which of the following has the highest bond dissociation energy? All right. Bond dissociation energy in molecular orbital terms is which one has the highest bond order. Right? High bond order means stronger bond. So if we have these to choose from, we have N2. This one has 1 negative. This one has 2 negatives. This one has 1 positive. And this one has 2 positives. Okay, so we can use the same molecular orbital structure for all of these. It's just how many electrons do in position. So if we go from start from the 2 p's, let's see. Yeah, that's going to be mixing. So this has a pi, 2p, and a sigma. Let's see. No, 2s. Excuse me. There I go again. 2s, 2s. Then we go to pi 2p and sigma 2p, and then pi star 2p and sigma star 2p. That should be enough. We're starting off here with the number of electrons would be 10, right? 10 electrons with this one. We're going to add 1 to this one, or add 2 to this one, subtract 1, and subtract 2. So those are the number of electrons that we're going to put into that structure. All right, so this one has 2, 4, 8, and 2. Right? This one has 2, 4, 2, and then we had to add 1 there. And this one will have 2, 4, 2, we'll add 2 there. This one will be 2, 2, and 4. And we take away 1 from the original, right? And then we take away 2 from the original, 2, 4, take away. Okay, if we calculate the bond order, this is going to be 2, 6, 7, 8. 8 minus 2 over 2 equals 3. If we add 1 and we add it to an anti-bonding orbital, it's going to reduce this one by half, because we're saying we're adding 1 more here, right? Which would make it 5 divided by 2 is 2.5. So whenever you add 1 to an anti-bonding, you decrease the bond order by a half, because it's divided by 2. Okay. Then we're going to add 2 more, which would go into this position, and that would decrease it by 1. So now we're down to 2. Then if we subtract 1, we're subtracting 1 from a bonding orbital, which would do the same thing. It would make 7 minus 2 is 5. So we're down to 2.5. So if you subtract 1 from a bonding orbital, you do the same thing as adding one to an antibonding orbital. And then this one would go down to 2. So the strongest bond is with A, N2. And it should be the shortest bond also. Stronger bonds mean shorter bonds. All right, 47. 47. Which of the following molecules or ions does not contain a central atom with D2sp3 hybridization? All right, so we got A, B, C, D, E. And we're looking at XEF5 plus, right? And IF4 minus, and SF6, and SEF5 minus, and all are D2sp3. Does not contain. Okay, so we're looking for the one that's not D2sp3. This means, electronically speaking, octahedral, right? 2, 3, 6. So let's see. Let's see the number of electrons. Let's do that first. So we have 8, and 5 times 7 is 35. That's 8. That's 35 minus 1. So that's 42, right? This would be for 5 times 7, 35, right? 35 plus 1 equals 36. And then 6 times 7 is 42, and 6 is 48 electrons. And this is also, well, this is 5. 5 times 7 is 35, and 6 is 41, 42. Okay, so we got our number of electrons. Xenon in the middle, 2, 3, 5. Fluorines, and fluorines, 2, 4, 6, 8, 10. So we got 32 left. 2, 4, 6, 6, 2, 4, 6, 2, 6, 2, 6. So 5 times 6 is 30, 40. So we have 2 left over. Right? That's 1, 2, 3, 4, 5, 6 groups. This is D2sp3. Okay. So this one has iodine in the middle. Probably have to go over there for some of them. And we have 4 fluorines. So if we count 1, 2, 4, 4 times 2, 4, 6, 8, 4 times 8 is 32. We got 4 left over. 1, 2, 3, 4, 5, 6 groups. That's D2sp3. Okay, SF6. 1, 3, 4, 5, 6. So that's all our fluorines here. 6 fluorines. So if you had 8 times 6 is 48. That's D2sp3 also. Okay, let's put this one over here. Se in the middle. 5 fluorines. And let's see. So that's 5 times 8 is 40, and we add 2 more. So that's 6 groups. This is D2sp3. And then we have Wait a minute. That's all of them, right? All of them are D2SP3. Yeah. That's it. They're all D2SP3. Everybody good with that?
Yeah.
Okay. All right. Let's see if we got any more. Get out of the way. Skip those. And we're down to number 60. Oh, we got a table. Okay. So I'm going to set up the table first. So we have molecules A, B, and C. Okay. And then we have electronic geometry. Here we have hybridization. And we have bond angles. We have examples. Okay. We're given this one for A is SP3. Okay. The rest of them, see, do I have another color? I used to. More than one color. Oh. Well, all right. We'll just have to go with it. This one's given. Right, the rest of them we deduce from the information in the question. All right, molecule B has two more effective pairs, electron pairs, than molecule A. So if B has two more effective pairs, they have to be D2, sp3, right? Molecule C consists of one sigma and two pi's. One sigma and two pi's. All right, how do you get two pi's? You can't have a pi until you have a sigma, right? So if you only have one sigma, both of those pi's have to be on the same, between the same two atoms, right? So that means you can only have those two atoms, which means it has to be sp hybridized because it's linear. Okay. All right. Now, what else? Okay. The geometry here, sp3, is tetrahedral. Right? This has to be octahedral. Bond angles. Tetrahedral are nominally 109.5 degrees. Octahedral. Well, let's see. Octahedral, sometimes I have to draw this one out. And these bond angles are only valid if every position is occupied by an atom. Right? If you have any lone pairs, then then you have to make allowances. So we would have like this. You would have right angles here. You have right angles here. And you'd have 180 between here and here. So this possibility would be 180 and 90. Linear is only one possibility, 180 degrees. All right, examples. Well, let's see. How about methane or carbon tetrachloride? Those would be good. Octahedral. How about, let's see, we drew one earlier. Let's see, let me go back. No, I'm not going to go back. I'll just use the one that's here. SF6 would work. And linear, how about carbon monoxide? Or dinitrogen? Either one of those would work. Okay. Let's see, we have any more? Yeah. Okay, we got, this one's kind of spread out. All right. I want you to draw molecular orbital diagrams for oxygen and nitrogen using molecular orbital theory and explain why the removal of one electron in oxygen strengthens the bond and the removal of one electron in nitrogen weakens the bond. Right, we did the nitrogen already. Right, and you can, I've got the molecular orbital set up here as the spread out, the complete version, but you could just as easily write the condensed version. That would work and would be able to answer the question for you. Oxygen has no mixing, nitrogen has mixing. So you're going to have a difference here in the way that they're set up. Right, with one oxygen on the right is no mixing, so it's going to have sigma and then pi. Nitrogen's going to have pi and then sigma. And then you fill it with the electrons, and these are just valence electrons because we're starting with the second period orbitals. And then answer the question. Why does removal of one electron strengthen the oxygen? Because we're removing an electron from an anti-bonding orbital, right, which increases its bond order. And for nitrogen, though, when we remove an electron, we're removing it from a bonding orbital, which decreases its bond order. So you can put those in your own words. Oh, is that it? That's it.